Welcome to all. Today let us talk about some interesting concept in physics called weightlessness. What is this weightlessness? See, every object which is having mass will always have its own weight when it is placed in the gravitational field. Okay. Here you have to note the difference between mass and weight. Okay, every object having mass m, okay, possess some weight equivalent to mg when it is placed in the gravitational field. Where here, what is g? G is the where g is the acceleration due to gravity. Acceleration due to gravity. Okay. See, whenever some object having its own mass is placed in the Earth's gravitational field, okay, what happens is it acquires some acceleration. A is equal to g. So according to the Newton's law, F is equal to ma. Okay, since A is equal to g, you have this F is equal to mg. We call this force as our weight. We call this force as our weight. See, this force is always towards the center of the Earth. Suppose that some a body of mass m is placed here. See, suppose that this point is the center of mass. So here, due to the Earth's gravitational field, okay, its mass, some force is acting downwards. Okay, this force is here, we call this downward force as the weight of this object. Okay, in the place of this object, you may take a person standing on the surface of the Earth. So his weight is always acting downwards to the towards the center of the Earth. Okay, why? Because see, gravitational force is working in this direction. So wherever you put some object in the Earth's gravitational field, okay, it always moves along these arrows. All these arrows are pointing towards the center of the Earth. This is what the concept of weight. See, how do you feel? In turn, instead of taking this inanimate thing, if you take a live person here, okay, what happens here? Whenever you take a person standing here of the same mass m, what happens here is if you put a person here, what happens here? Then, since he is a living thing, he feels some weight. He feels some force on him. How he feels this force on him? See, this is the surface of the Earth. Okay, here he is inserting some force on the surface due to the Earth's pulling. Okay, in this direction. This is the direction of Earth's gravitational field. So, some mg force is acting on this Earth surface. According to the Newton's third law, this surface is also exerting the same force on him. Here, we call this as a normal reaction, N. Here, the magnitude of this normal reaction is equal to the weight. Okay. See, whenever you have this normal reaction force non-zero, then only you feel your own weight. Here we have to understand this. See, here you are feeling your own weight because the surface of the earth is exerting some force mg on you. Okay, in the reverse direction. Okay, you are applying some force on the earth's surface due to the gravitation of the earth. This surface in turn exerting some force on you. Okay, the magnitude of that force, okay, normal force is equal to your own weight. Okay, this is a way of feeling one's own weight. You are feeling heavy due to the reaction of this surface. Okay, the same thing applies to you whenever you are there over in a space station, or whenever you are there in a rocket. Okay, the same thing applies for you. Suppose that for a moment these two things are also stationary. Instead of standing here, suppose that that person is standing in a stationary rocket. That person may be standing in a space station. Suppose that these two things are in a stationary mode. Then here also, you see, as you go away from the earth, what happens? G goes on decreases. Gravitational acceleration decreases. Why? Because attraction of the earth decreases as you move away from this earth. Okay, see, this earth, this matter itself is a source of attraction. As you move away from this source, what happens generally? The attractive force decreases. See, whenever you consider these two things, they are somewhat away from the center of the earth, but still they are in the gravitational field of the earth. So the person, see, in this rocket or in this space station are also feeling their own weight. Is there any difference between the weight of the person here on the surface of the earth and here on the surface of the rocket or on the surface of the space station? Can you guess the answer? See, here the difference may not be that much large, okay, to distinguish between this value and this value, okay, unless otherwise you take this space station or rocket far away from the Earth's surface. But definitely, since the gravitational attraction is small, since G is small, see, always you see that this N normal reaction C is equal to some, see, I'm writing the same formula. Now our new G value is G prime at this point, at this place. Okay, say this is a position A, say this is a position B. Okay, at the position B, I am assuming that the acceleration due to gravity is G prime. Then what is the relation between G and G prime? See, this G prime is always less than G. Why? Because B position is far away from the Earth's surface or the Earth's center. So naturally what happens is, here, this mg prime, okay, that means, say this is n prime if you want, see this n prime is equal to mg prime will always less than the mg. See, m is not changing as a person moves from here to here, but what is changing here? G is changing. As G changes, the weight of the person also changes. Okay, see, this mg value is now less, mg prime value is now less than this mg value or n value, because G prime value is less than G. Why? Because G prime is the value of the acceleration due to gravity at a place far away from the Earth center. Okay. Yeah. See, here also the person is feeling his own weight. Here also the person is feeling his own weight. Here also the person is feeling his own weight. But what happened from position A to position B? Here at position A also the person is stationary. At the position B also the person is stationary. See, but what is changing from A to B? The person is same, his weight is same, but just we are changing his position. Due to this position, what is changing here? G is changing. Yeah, this position A is very near to the earth center, position B is somewhat away from the earth center. That's why acceleration due to gravity at the position A is large compared to the acceleration due to gravity at the point B. So, naturally, a person standing at position B feels somewhat less weight compared to the weight at the position A. Okay, I think you understood this. Now, the question is, can we make a person's weight reduced to 0? This is one important question. When do you lose your 100% weight? Here, now I am going to talk about loss of 100% or losing of 100% weight. Okay. See, according to the physics, this 100% weight loss is possible. 100% weight loss is possible. But whenever you go to the doctor, see, and you ask for the recommendation of reducing your own weight, here you do not get this much promise in there. Okay, but in physics you always get the promise that your weight always decrease 100%, provided some conditions are maintained. Okay, but actually whatever the diet you take, reducing of 100% weight is not possible. But in physics, whenever you maintain certain circumstances, it is possible to feel weightless. You are feeling almost you are flying. Okay, this happens in that. At one time, what happened is the cable of the lift is broken. Yeah, see, this is a cable which is attached to the lift. Okay, under the normal circumstances, this rope will be intact. Okay, your wheel should be there. It is connected to the motor, and as this wheel rotates, this may be either pulled up or pulled down. Okay, this is what the principle of working of the lift. Very simple. See what happens. Suppose that your lift is going up. Suddenly, what happened is this cable of the lift is broken. Then what happens here? Then you lose your weight 100%. Then you feel that you are almost flying. Okay, suppose that if this is going to happen, then you will be just feeling free. That means you are just floating off the surface of this lift. Okay, of course this does not happen for a long time, so you may not notice that, but momentarily you notice your 100% weight loss whenever you are placed under this situation. So according to the physics, 100% weight loss is possible. What are the other examples of losing the 100% weight? You will lose 100% of your weight if you are placed in a satellite revolving around the earth. Okay, how it is possible there? How it is possible even here? So here you may lose your weight 100%. So what is the meaning of losing total weight? Normal reaction is 0. This is a condition for the total weight loss. Here you are not at all feeling your own weight when n is equal to 0. This happens in this case, and also in the case of an artificial satellite, artificial satellite revolving around the earth. Okay. Otherwise, suppose that a space capsule is also rotating like this in one orbit. Then what happens if you are there in that space capsule? What happens is you almost feel weightless. That means you are going to lose 100% of your weight. Okay, that can be supported in all ways in the physics. Okay, here how this is happening? As far as we know that. Definitely you are going to see the variation in your own weight, okay, due to the position change. Here we observe that so the same person is feeling some weight here and feeling some lower weight here. Okay, so it is we have seen that the weight loss is possible even though your mass is not changing. Okay, your weight loss is permitted. Here this is permitted to the extent that your weight, that means your normal force acting on you, is equal to 0. Okay, suppose that your weight is some 60 kg. Whenever you are there in such a lift, now what is happening to your weight? 60 kg is going to the 0 kg. So the 100% reduction in the weight is taking place here. Here also you are observing the 100% weight reduction. Okay, suppose that some object is here, okay, in this satellite, some bolt is there. Suppose that it is of weight some 50 grams. Okay, whenever it is put in this orbit around the Earth, immediately what happens is its weight becomes 0 grams instead of 50 grams. That means complete weight loss is taking place. If you take this as a space capsule, okay, and you consider one person in that space capsule, whenever the space capsule rotates around the Earth, what happens is immediately he loses his weight. Suppose that if his weight is 60 kg, immediately his weight is going to register as a 0 kg. 0 kg. Okay. Here, what is the meaning of this? Here, there is some chance for misunderstanding this weightlessness. Particularly, you may see here that too, particularly in this second case. That means for a person in a space capsule or an object inside the space satellite. Here, actually, what happens is whenever there is no gravitational attraction, then what happens to your normal force? N is equal to mg is equal to how much? Whenever there is no gravitational pull, you are going to get 0 normal force. That means 0 weight. Here you may assume that as this satellite is far away from the Earth, okay, so you may assume that g is equal to 0. So the weight of any object in the satellite or any person in the space capsule is going to reduce by 100%. But that is not correct. Even though the satellite is far away from the Earth, g is not 0. Here g is not totally reduced to 0. Some weak gravitational force is acting on this object which is placed inside the satellite or a person who is there in a space capsule rotating around the Earth. Okay, that we have to know. Since there is some non-zero g, we always expect some non-zero weight. Then how this weightlessness is possible here? That is important to know. Okay, that is important to know. See, here also, this lift is obviously on the surface of the Earth. Okay, here also g is not equal to 0, but you are going to get normal reaction is equal to weight is equal to 0. You see the magic. We are expecting the weight to be 0 unless otherwise the g is 0. But in these two cases, g is not 0. Then how you are going to get the 100% reduction in your own weight? Yeah, this is some amusing thing you need to know. Here, how this is practically being achieved in these two circumstances. Okay, that need to be explained. Here, always we have to see that what amount of action reactions are taking place here and here. Okay, in order to understand the second case, okay, it is better to go for the case 1. If you are able to understand the cable with the broken lift with the broken cable, okay, then it will be very easy to understand the weightlessness of an object placed in a satellite rotating around the earth. See here, whenever the lift is not at all moving, that is the same case here we are already discussed, there will not be any change in the weight of the object with mass m. If this lift is not at all moving, normal reaction is equal to weight is equal to mg. Okay, there is no difference between the weight on the earth and weight in the lift, as long as lift does not either moves up or moves down. Here there are two ways of moving the lift. What are they? Either the lift may be moving up or the lift may be moving down. Two cases are there. Okay, here moving up. Suppose that you are going from the first floor to the fourth floor. Okay, your lift is moving up. Then what will be your weight? Your weight is always equal to the normal reaction. That means how much of force is being exerted by the floor of the lift upon you. That is your own weight. Okay, that you are feeling as your own weight. Here now let us calculate the normal force in this case. Okay, see, this is a lift. Suppose that this is a lift. Okay, we are already assuming that it is going up. See here, the acceleration of the lift is upwards. Okay, now see, this is some object here, a person. You consider the person here. See, this person is having some mass, so his weight is acting downwards due to the pull of the earth. See here, this is one type of force. Weight is one type of force. Okay, this is mg. Now, what will be the normal reaction? See, the normal reaction is always equal and opposite to this weight. Okay, so the normal reaction will be, okay, acting upwards with the same magnitude. Okay, here, whenever you apply the Newton's second law, F total force, okay, F total force is equal to ma. Acceleration is the acceleration, okay, of the lift or the person who is moving along with the lift. See, what is this? This force or this acceleration, okay, here shows you the direction of movement of the lift. Okay, this is here going to influence this extra factor, this motion or this acceleration, okay, will definitely going to influence this normal force. Here this total force is now written as, see how many forces are there. Here this downward force and upward force is there. Okay, here let us see this as, okay, normal force, okay, N minus, if you take this direction as a positive x direction and this direction will be negative x direction. Suppose that this is the x-axis. Here you always have all positive values on this side. Here you always have negative values on this side. So whenever you take n positive, what you have to do? You have to take w as a negative. Okay, or what is w? mg is equal to ma. Okay. Now I am going to substitute the formula for W here in order to avoid the confusion. What is W? mg is equal to ma. See here, then what is normal reaction? If you take this mg term to this side, you are going to have ma plus mg on this side. Whenever you take m common, here you are going to get ma plus g. As I already told to you, normal reaction itself the weight. Normal reaction itself is a weight. So under these circumstances, so the person is having the weight is equal to normal reaction is equal to ma plus g. You have to note this. So far, we considered the weight as mg only. Since weight is equal to normal reaction, and in this particular case the normal reaction is equal to ma plus g, so the weight experienced by the person is now not mg but ma plus g. What is the meaning of this? Since mg value is always less than the mg plus a value, see, since mg is less than ma plus g, okay. Why? Because something is going to, a is going to add for this g. So this initial weight mg, okay, is always less than the ma plus g. That means what is going to happen here is, see, earlier you have m is equal to mg whenever the lift is stationary. Okay. Now, okay, what is happening? Your n is becoming ma plus g as the lift moves up. Okay, as the lift moves up. See, you compare these two things, n1 and n2. This is the ordinary weight. Whenever the lift is stationary and the person is stationary, his weight is just mg. Now, whenever he is in the moving lift, what is going to happen to this normal force is going to increase by ma. So, the person feels the more weight than before. Okay, suddenly he feels that his weight is increasing. His weight is increased. Momentarily, he feels that he is weighing so high. Okay, not so, but so high. Okay, so what is happening here? The weight that appears to that person is going to increase as the lift goes up. Okay. See here, we already know that even though there is no motion in the lift or in the racket or in the satellite or in the person, so here we are going to, we are already noticed that as long as they are stationary either on the earth surface or on the surface of a racket or space station, okay, then we definitely observe the change in the weight of that person. As that person is lifted from the earth surface to a place away from the earth surface, okay, he always feels as if his weight is going to decrease. But in this case, what is happening? Whenever the lift is moving up in the Earth's gravitational field, he suddenly feels that his weight is going to increase. Okay? Right. See here, actually his mass is not changing. Okay? But this normal reaction magnitude is changing. That's why his apparent weight is going to increase. Okay? As long as there is no motion in the rocket or the spaceship or the observer, okay, what we observed is the weight is equal to mg only. If you are considering only a place just above the Earth's surface, there also the person is feeling the same weight mg. But whenever you take him far away from the earth, then he noticed that some amount of decrease in his own weight. But in this case, what is happening? He is feeling that suddenly he is going to weigh more and more. Okay, right. Here, what is happening in this case? We say that the apparent weight of the person, apparent weight, that means the weight which he feels, apparent weight is going to increase. Yeah, this only applies to this particular case. Now you consider the case of lift moving down. What happens when a lift moves down? The cable is still intact, but it is moving down. Okay, now in this case, let us see what happens here. Here, case B, moving down. Lift is moving down. Yeah, here again you take the lift. Okay, you take a person inside that lift. Suppose that now this lift is moving downwards. Suppose that person is coming from, say, some 4th floor to the 1st floor of the lift, or from 8th floor to the 1st floor of the lift. Then what happens to his weight? What is his feeling about his own weight? Okay, now let us analyze this situation. Here the acceleration is downwards as the lift is moving down. The mass of this person is m. Okay, so how much force is acting downwards? Mg force is acting downwards as before. It always acts normal to the surface. Similarly, this is a weight now. Usual weight. This here in the opposite direction, the person always have normal reaction. Okay, normal reaction. Let us just say this is a normal reaction. Okay, the magnitude here, what you have to note is the normal reaction is not always equal to the weight. That depends upon the circumstances. That's a very important point you have to note. Okay. See, some normal reaction will be there. This is a result of all the other forces acting on that person, including his own weight. Okay, this you have to note. Here, how to modify this equation? Okay, here also you are going to apply Newton's second law, F is equal to ma. But how to write this net force here? In this case, okay, again you take this direction as a positive x direction. Okay, and this direction as a negative x direction. Then what happens here? All the forces pointing upwards are taken as positive. Okay, here this n is one among the forces making this F. See, this is the net force. See, n. What are the other forces are there? In order to get the net force, we have to include all other forces. See, apart from this n, mg is also working. Since mg is acting downwards, okay, you are always going to take this as minus mg. Okay, weight. Okay, w. What is this? W. I am writing mg for w. So here you have MEA. Then how to correct this here? We have to write this according to our sign convention. This term, RHS term in the physical term, MA. Since acceleration is pointing downwards, all the downward pointing arrows are taken as negative according to our convention. Since we are taking all the downward arrows as negative, here what we have to do is we have to put minus sign here. Okay, why? Because this force is acting downwards in the direction of a negative x-axis. So what correction we have to do here? For this n is equal to a, we have to write this f is equal to now minus ma, and there is no change on this side of this equation. Okay, n minus mg is same here. Okay, here what we are changing here, instead of writing plus ma, we are writing minus ma. Why? Because a is flipped downwards. Your lift is suddenly coming down. Okay, this you have to understand. This is a very important step. Here the sign convention is important. Okay, you have to maintain some rigid sign convention. So now what is your n? Come on, tell me. Whenever this mg term goes to this side, on this side it is minus. Whenever you write this on this side, it gets, you have to change the sign. So I am writing mg on the other side, not as minus mg. Okay, on this side you already have ma minus ma. Now take m common, then what you are going to get inside the brackets? G minus a. Now you see the expression for the normal weight. Actually, what is n under the normal circumstances? It is mg only. Here what is happening? It is going to decrease by ma. It is going to decrease by ma. Okay. So what is happening here? The person feels weightlessness here. The person is going to feel the loss in his own weight. See, when the lift is moving up, he felt that his weight is suddenly increased. Whenever the lift is moving down, he felt that his weight is going to decrease. Okay. So all these things are permitted in the physics. All these things are not in the common sense, or not in our day-to-day discussion of the weight, but in terms of physics, all these things are permitted, exactly permitted. Okay, all these things are permitted by the physics, but not by the medicine or whatever that may be. Right, here, yeah, in this case, since the normal reaction is somewhat less than the usual mg, we say that the person has lost his own weight by some percentage, okay, not zero. In these two circumstances, the weight is changing, okay. In the second case, the weight is decreased, but not up to zero. Now let us see when the person loses his entire weight. When this 100% weight reduction takes place. Now we are going to the case C, the third case. Yeah, we are already having the diagram here now. You see here, this one. Yeah, I am talking about this case C now. Here, what is happening is a free fall of the lift. What happens when the lift cable of the lift is broken? This is a free fall. It falls freely in the gravitational field. The person also falls freely with the lift. Now you see what is going to happen here. Now still the lift is moving downwards. You are already having the expression for the downward motion. Now you may use this already derived expression here. Okay, the same equation is applicable here. mg minus a. But how many? See here, what is this? What is the value of this acceleration in this case? See here, this acceleration is taking some special value called as g. Why? Because whatever the acceleration now this lift and this person is having due to the gravitational attraction of the earth. So this a now assumes the value of g. Now in this case, acceleration of the body is becoming equal to the acceleration due to gravity. So whenever you put this condition here, you are going to get mg minus, what is a? It is also g. So g cancel. So now you are going to get m into 0. Okay. Here, what is your normal reaction now? N is equal to m into 0. So here you are getting 0 n. Your normal reaction is taking the value of g. As I already told to you, whenever the normal reaction becomes 0, that means here the bottom of this lift, as long as the lift falls freely downwards, what happens here is this bottom portion of the lift does not exert any force. Why? Because you just calculated that normal reaction is 0, n is equal to 0. Whenever n is equal to 0, whenever there is no upward force on the person, then he definitely feels as if he were lost his 100% weight. So in this way, the complete weight loss of a person is possible in physics, depending upon the circumstances. Whenever you place a person in a freely falling lift, what happens to his weight? 100% loss in his weight takes place. He feels free. He feels as if he was just flying like that. Okay, right? This happens to this lift as well as that person. Now you see, there is no direct relation between, or contact. Sometimes we call this N as a contact force. Whenever there is some contact, then we have some non-zero contact force. See, the other name given for N is a contact force. Okay, here, whenever there is no contact at all, then there will not be any contact force or normal force. Whenever there is no normal force, what about the weight? Weight is equal to normal force is equal to 0. So in this way, the person is going to get 0 kg weight. Okay, suppose that his actual weight is 60 kg. But whenever he is placed in such a lift, his weight automatically falls to 0, from 60 to 0. So here 100% weight loss is taking place. Okay, here suppose that this is the bottom of the lift, this is the person. Okay, suddenly when the cable is broken, then what happens is no longer this person, okay, will be there on this surface. The contact between his feet and this surface is lost. Okay, there is no relation between this person and this object. Okay, you have to imagine, you have to understand one important point here. This acceleration due to gravity does not depend. Influence of gravity on the objects does not depends on the nature of the object. Here the lift, the material, this cable and this person is same here. Okay, both of them are falling down with the same acceleration called as acceleration due to gravity. So there is no need to maintain the contact between the legs of this person and this surface. Okay, now this lift may be going like this, falling like this, and this person may be falling like this. Okay, there is no contact between the surface of the earth and this person. As long as there is no contact, there is no question of arising the contact forces. That means normal force is equal to 0, so the apparent weight is also 0. So in this way, the 100% weight reduction is possible in physics. Okay, now this is a very important point you have to understand here. Why he is losing his entire weight? Okay, this is the magic of the gravity according to the Newton. This is the magic of the gravitational field, nature of the gravitational field. In the gravitational field, if you toss a coin or a feather, both of them are going to fall with the same acceleration called as acceleration due to gravity. That means if you are dropping them from the top of the hill, both of them are going to fall on the earth at the same time. Okay, unless otherwise there is no air resistance and other things. This is what called as a Galileo's experiment. Okay, in this way, the weight reduction, 100% weight reduction is possible here. Now let us go for the other case. Okay, the second case, the weight loss of a person in the artificial satellite. Okay, now let us go for this second case where one may lose his 100% weight. Okay, now let us go for the second case. Okay, man inside a space. Okay, it's a shuttle or whatever it means, space capsule. Okay, yeah, now this is the earth. Okay, all our satellites or space capsules, okay, are going to revolve like this. That means we are going to put that satellite or the space shuttle in one particular orbit. Okay, this is what is this? This is the Earth. Okay, this is the satellite or the space shuttle. See, suppose that you imagine one person in this space shuttle. See what happens to his weight. As I already told to you, even though this satellite or the space shuttle is far away from the Earth, the gravitational field is not zero. So definitely you must have some original weight, okay, depending upon the g value at this position. Okay, right. So there is no question of having 100% weight loss. Some weight loss will be there depending upon the height of the orbit. But here, according to the physics, 100% weight loss of any person is possible here. How it is possible here? See, as I already told to you, this is only possible in a free fall. You know that the lift is falling freely in the Earth's gravitational field. But where is that free fall here? This is very important. Where is this free fall? How many forces are acting on this satellite here? See, you know that the satellite or space shuttle always have some tangential velocity. Okay, we call this as the orbital velocity. So this space shuttle or the satellite is revolving with some particular orbital velocity. Okay, now my question is whether this satellite is in the Earth's gravitational pull or not. If there are no other forces, according to the Newton's first law, this satellite should have moved in the forward straight line direction. But you see here, this is a curved direction. The path is curved here. Why this curved? Why it is moving in the curved path or the orbit? See, this bending of the path, this change in the path is taking place due to the gravitational pull of the Earth. Since the gravitational force is acting downwards from time to time, okay, the satellite is pulled downwards. Okay, in this way, the satellite is now in the continuous fall in the Earth's gravitational field. Where is the evidence? The path of the satellite is not the straight line. The path of the satellite is this circular orbit. Okay. Why this path is in this shape? Okay. Why it is revolving in this circular path? Why? Because there is only one force acting on the satellite called as a gravitational force. Okay. So here, as you have seen here, there is only one force acting on the lift whenever it is in a free fall mode or whenever its cable is broken. The same thing you observe in case of satellite also. But here, why it is not just directly falling down? It is falling down continuously. Why? Because it is having some tangential velocity. This is a very important thing. You have to only upward and forward motion. Here, the satellite is given some tangential speed. Okay, that's why instead of falling directly on the Earth, it is continuously falling towards the Earth. This is a very important thing you have to understand. If you are able to agree that this is a free fall in the Earth's own gravitational field, okay, then you simply conclude that the weight of any person in this satellite or spacesuit is equal to 0. Okay, in this way, you can easily explain the 100% weight loss of a person in a spacesuit or satellite or an object in a satellite. See what here we have to compare this third case in case of the lift and this case. Whenever you confirm that this third case, free fall case of the lift is equivalent to the motion of a satellite around the Earth, you immediately conclude that the normal force is 0, hence the weight of the person is also 0. Hence the weight of the person is also 0. This is very important thing. see here, we may very much confuse about the weight loss, 100% weight loss in case of a person who is inside of a space station. Why? Because even if you say that, even if you agree that his weight is 0, you may try to explain this in some other way, but which is actually wrong. Since we feel that whenever the satellite, since the satellite is far away from the Earth, since we assume that naturally, since there is no gravitational field, since there is no G, so there is no W. So in this way, mistakenly, we always try to explain the concept of 100% weight loss in case of a person in a space shuttle, but that is not correct. Here, how to explain this? Still there is some G here, so still is having some weight. Considerable weight reduction takes place whenever a person moves from Earth to the space shuttle, but still his weight does not reach it to 0. His weight is now going down to 0 because of the motion of the space shuttle in the Earth's orbit. Okay, as a physicist, okay, not as a physician, as a physicist, you may say that 100% weight reduction is possible. Okay, thank you.